University seminar for today. It is my pleasure to introduce Dr. Deng. He's a principal research scientist at Microsoft, Redmond, and prior to that, he was had experience in academia in the University of Waterloo. He has been a key contributor of the use of deep learning in speech recognition and in the industry, and he's going to talk about that today. So please welcome.
Okay, thank you very much. Is it on? Yeah, okay. So again, so today's topic is deep learning. And I actually tried to, well, actually Henry was in my talk a couple months ago, so I completely changed everything so he won't get bored. So there's so many different perspectives of talking about the same topic. Yeah, indeed, yeah, very, very different. Yeah, exactly, yeah, because this is actually talking to speech recognition crowd. And normally I give this talk to various other groups like speaker recognition, sometimes to speech translation, NLP a few times. So I actually have to introduce a lot more, some very basic stuff. But now, I think for this crowd, I go a little bit fast. So I'm going to be quite kind of overview type. So hopefully just to give you a global picture to show how promising this technology is. Hopefully, I have seen in the morning that quite a number of people here already started exploring this technique. There are so many things that needs to be done. So the agenda here is follows 4 quadrants. I'll give you some background. Actually from speech recognition perspective, and then tell you what this deep learning looks like and how it has been developed and some history of how it entered into speech. That was about 2 or 3 years ago. And then I'll tell you some evidence to show what kind of success that deep learning has achieved in speech recognition. Hopefully from this you can inspire how to do some further work, and I'll tell you the next way of innovation to come. And that actually, so this one actually ties into everything else here. So every time I talk certain things over here, you might say, oh, this doesn't make sense, and everything will make sense after you go to the last part. Okay, so this one ties into some very old workshop done right here. That was, maybe many of you were not even here. Jack, you were here in 98. I think Sanjeev, you were here. So I was actually doing, I think Tom, you were here, 98. You're here. Oh yeah, okay, you're in the same team. Okay, great. Nice to meet you. So things started from there. So the result of that workshop, for which I think John Bridle and myself were the technical leader. We got a few people here doing this. What's a little bit at the end, what I would call is disappointing, right? In the sense that we try to apply articulatory, like realistic speech generative model to recognition, trying to overcome many poor assumptions of a hidden Markov model, and try to use the long-term dependency, all things we know about speech into the system. And that actually this is the name of the project. And at the end, number one, decoding becomes so difficult. So at the planning meeting, we decided we just do second pass decoding, okay? And that's a big mistake. And then of course, we generate M-best list, and then we rescore them. And I'll tell you why it's a big mistake and why this new deep learning overcome that mistake and get huge success. And the second part of that workshop was to rescore them. So in my team, I was actually using generative model to rescore individual ones. I think in John Bridle's group, he also got 3 or 4 people doing. I think you were in both, right? I was using a different way of embodying the same kind of methodology to do scoring. He actually at the end got virtually identical result we have. So we get reasonable gain. I think of 3 or 4 relative % compared with the original HMN. And was 3% relative is very disappointing. And then I think John Bridle totally got disappointed. He decided not to do any further. So a few years ago, I told him something good is happening, and he didn't believe it. That actually, I'm going to go to show some of the history of here. He didn't believe. He just said, "Well, just hidden Markov is good enough." Essentially, so that is what I call disappointing. Okay, so but the insight that we put into that project and the basic philosophy underlying all this, deep speech model is very wide. So the essence of that model was to explore, deep dynamic model, which are natural for speech. For example, in terms of speech production, you have all sorts of structure in the speech production process, all the way from semantics and for phonological coding, from phonetic decoding, articulate dynamics, speech, all the way. And then these are other things we added after I went to Microsoft. So I think in that workshop, we mainly, focus these 2 or 3 layers, deep layers. And in John Bridle's model, he also, focused on this, and he used kind of neural network to train them, which is very hard to learn. And if you knew how to learn it now, at that time, things would go a lot better. But anyway, that was the history. And also, in terms of speech production, we also have many layers. But anyway, so this slide just to show you the speech production and speech precision indeed have deep layers. And that actually, to me, is a very natural way of modeling speech to do either speech recognition or synthesis, either way. So now, so at that time, so this is actually the big model that I built after a few years. But at that time, typically we go about a few layers. So think about this as the phonological encoding. And at that time, I think at that time we were just using phoneme. It's very, very simple. But in realistic case, this is multi-dimensional phonological features, like distinct features stuff. And this layer is the target, articulatory target, where each dimension of this phonological, sometimes people call articulatory feature, are encoded in terms of numerical target, in terms of distribution. And that controls articulate dynamics. And like in 1998, I was using a common filter to do the decoding. This is the approximate solution for this rigorous Bayesian network learning. So when I went to Microsoft, we used several different techniques, variational Bayesian, and we got some better gain than the one I did over here. So I've been very persistent in doing this. And then once you get articulate dynamics, which is very important, that those are continuous in terms of from state to state, which is missing in speech in hidden Markov model. And then from this, you get a very highly nonlinear process to go to acoustic, which is distortion free. And then later on, if you want to do noise robustness, you add some additional factors here. So for example, these are the distorted acoustics through channels, microphone distortions. And then you got this noise factor, and then there's a channel factor which tie across the time. And you get also non-stationary noise. You get this part. And this, together with the clean speech, gives rise to observation, which is noisy speech. Now the goal of speech recognition that actually want to estimate what the linguistic contents you have, given the noisy speech, that's called the inference. And anybody in graphical model looking at this diagram, actually in Microsoft, after I moved Microsoft, I'm still very interested in working on this. So this David Heckman, he's he's kind of one of the pioneers in this area. He immediately looked at this, he said, Lee, forget about this, it's too hard to decode. You should use all sorts of approximation or you just give up. So I said, fine, let's do approximation as much as possible. But note, this layer, so in John Hopkins workshop in '98, this model was, we use neural network, MLP neural network. I think, Terry, you probably, I don't know whether you implement that part. Or Mike Schuster, you one of guys now who went to Google to do all these things. So the same team member. He actually implemented really nice neural net. It's about 3-layer neural net. At that time, my personal experience in doing this is that sometimes it gives good prediction, sometimes it doesn't. So the learning is pretty hard. I know. I got first taste on this kind of the quality of neural net. It's very hard to learn it, and especially the target is hidden here. It's actually more complicated than the real network now we are using, because the target is coming from common filters output, which is variable to begin with. It may not be precise. So we just integrate this whole thing. So I wrote down all these EM estimation formula, and then we apply them in the training. And then in the decoding, we just use, and we even use HMM segmentation to guide our decoding, and then we do evaluation. So we get a very, very small amount of gain here. But anyway, so this, so once I moved to Microsoft, I worked with a group of very talented scientists. So like Hagai Elias, anybody who is in machine learning will know. He's the one who invented Bayesian variational Bayes technique. So he was just sitting a few doors from me. So we said, well, let's use all the best technique around in approximate inference in the learning for this. So we actually use this multimodal variational learning. And we try. So this is the kind of simplified model for essentially the same model as the one I did at Johns Hopkins '98. It's just much better learning that we apply in terms of more principled way of learning rather than doing, segmentation and then using Kalman filter, which is much more empirical. And indeed, we got a certain amount of gain. And this is actually one of the project we actually did for DARPA's EARS project when Jack was around. We didn't have a big team because we didn't actually get our market doesn't allow us to get any funding from government. So they said that, well, you try to get a few volunteers who would like to work with. So we got a few people working together, including this guy. And then at the end, we happened to be in this called the novel approach team rather than the core. So we don't have to spend all the engineering to do it. And then it turned out we got a lot of insight out of this. So we understand what the problem is. So the key insight coming from that kind of DARPA EARS project is that this deep structure is very important because when we analyze error, we look at exactly what, at that time we even have to make an approximation to simplify that from articulate structure, which is hidden, you can see, into what's called vocal tract resonance, which you can see, it's kind of Foreman-like. But the difference is between the regular Foreman that most speech scientists know about is that we got the hidden Foreman, and that Foreman actually can go into the closure part or all kinds of speech sound, not just vowel sound, because we use physical property of vocal tract resonance. So every time you close your mouth, your resonance is still there. It just doesn't get revealed in the acoustics. Right? So that part is continuous in the same property as articulation. And at least for that one, if we use the resonance rather than the articulatory configurations, we actually can do some debugging, at least. Something, if we do decoding, we might be able to see, well, in the vowel part, at least we are decoding right because it captures the formant. Right? But in some consonant closure part, we couldn't even see that. In some voice, this part, the resonance could be very low, but some acoustic energy can be high, so we can just use our guess. But this one helps a lot. So we realized that, doing this generative modeling using Bayesian net, we actually can not only model some hidden internal deep structure, but also we can diagnose them. But once we go to neural net, it becomes much harder. I'm going to show you. So this is one of the side projects out of this generative modeling, using Bayesian network. So if you were to do inference for this project using this variational Bayesian, you actually given acoustic observation, for example, capsule coefficient or PLP, whatever acoustic parameter you do inference, you actually will get resonance out of this. So one of the things I really like that model was that look at the resonance we can get. They're very, very similar to the formant. Every time it hits into vowel, it actually captures the formants. Even formant transition, very, very sharp formation, we capture really nice. So I think this model has really a great deal of power of doing this. And then, of course, once you get this consonant sound, essentially it just smooths over here according to the articulate dynamics we assumed that apply. It's essentially the second order dynamics. It's exactly the same kind of dynamics that we did in our workshop. And then this is good. So at one time, actually, I decided, wow, even if that project on SpeechBoard failed, disappointing result, similar, the final result is similar. We actually try to do decoding, direct decoding on this. And so we get very, very extremely good engineer to help me to write decoder for this model. We wrote it, and the result is, and we have to expand our letters in a very, very big way in order to do this decoding. We didn't really get much better result than the workshop. Now, the side project of this is that we got really the best quality of the formant tracker you can ever possibly have. So I think, for Microsoft, I don't have to contribute to product too much. So I said that, well, one of the nice things about doing this is that I can make it a tool to make this formant decoder. So actually, I worked with Abir Awan in 2006 in the summer. So I went there to supervise a group of students to actually use the result of this decoding, for the timid. So we use the hand to correct all the labels. So we got about, 700 sentences with hand labeled resonance, and that become the formant track database. So now, I think in Europe, I don't think in US, not many people are doing that. So anybody who is doing decoding, formant tracking, they use this database to evaluate. It's the ground truth for formant tracker. Before, nothing like that happened. So this is very nice. So I'm pretty happy. But at the same time, decoding is so expensive. I decided, to abandon it. So yes. Okay.
You're not talking industry scoring recognition kind of result.
It's the reckoning result. It's disappointing.
But what about the format tracking? Is that
Format tracking is a very, very good result.
switchboard also?
No, format tracking, we use that for many different tasks.
Okay.
For format tracking, there's no evaluation of format tracking, all right? So we look at on the TIMIC, and also we apply that for Wall Street Journal. For all the speech tasks, they all look just as quality. It's almost as good as this. So this, very similar to this. So I think in my website, I have this, database which actually directly use this technique, and also with the hand corrected format checking that people use to evaluate their format checking result.
Ask you a slightly detailed
Yes.
question. So, in the model that you showed, the top level was your transcript and Y was the observation, and X is this hidden layer where you track these.
Yeah, correct. Yeah, correct.
So, if you take an utterance and give it the correct transcript,
No.
give it the incorrect.
No. So I have to correct that. Now for format tracking, I actually average out. Well, actually, there's another layer. It's called the target layer. I didn't put it here. There's a target layer here, and the target layer, I just make the target to be average. So the target is not form dependent anymore. Its target is just average: 500 hertz, 1,000 hertz, 1,500 hertz. And
Okay, so I thought you might have tried something different, namely put two different hypotheses to create the target. And actually, I will show you the reconstruction error, right? It's for the right target,
I see.
the right transcript, the format trajectory will fit. And for
I
the
see.
transcript, they would not fit. So I thought maybe the likelihood might show you.
Yeah, we didn't try that. Yeah, that's a good idea to do that. If once you do that, you can. I mean, the whole point for form checking, you're not supposed to assume that you know the phoneme sequence, right?
Because my thinking is that
Yeah.
the model is essentially a good format tracker. The fact that it would then work
You are correct. Yeah, that's correct. So if we were to use this, if we were to use the form sequence over here, the format tracking result is much better, much better than just taking the average. Because on average, you still use the data to estimate the target. I think Joe Olive actually has a paper with his colleagues published just 2 or 3 years ago that make use of this, and the result is very good. But don't quite trust that result, because the reason why I say that is because it uses this information here. You get much better result. If you look at the diagram, you say, oh, that's why you get the perfect format tracking, because they use this information. If I use this information, you will get much better. But the real format tracker really shouldn't use this result. Shouldn't use the phone information, because you get the signal coming in there. So in our format tracking here, we just simply wipe out that layer and then put the average resonance, F1 500, and then of course when you get the capture data coming in there, you will adjust, 500, it becomes 400, sometimes 800. Okay, anyway, so those are all the history. Now I'm going to show you how all this line of work enters into deep learning, which is a very, very different perspective in capitalizing on the deep structure in speech. Okay, well, so this, are you able to see that? Well, so I said that it's promising result for TIMIC, so I used that for TIMIC result. So this is a paper written to summarize, that's published in 2006, out of the work done about 2 years. It actually moved from, so that's HTM, a hidden trajectory model, which is extension of the earlier model. So these are all the kind of, the overlapping windows in terms of interaction across different phones. You look at, they're all local, right? So of course in speech is local. In NLP, the correlation actually can jump for long distance. In speech, typically it's local correlation. And the result actually, if anybody is doing TIMIC phone recognition, so this result will actually get 75% accuracy, a little bit higher. Whereas in HMN, people typically don't go anything beyond 72%. So, but now the key is that if you use the deep network I'm going to talk about, it jumped to 77%. And it is this 2% of difference that amplifies into huge success in switchboard, get about 33%. Relative. So this is relative about 10%. So one of the amazing thing about the deep learning, which I'm going to talk about in the second part of this talk, is that most of the gains that I found in TIMIC over here gets expanded much more. It does because well, one of the folk laws in speech is that usually for small tasks, you may not translate to larger tasks. That's most of the time it's true. And that's because the variability here is smaller than the real task. Now, using deep network, it's just opposite. You expand that because the reason why there's a huge, we tried so many different tasks. In the beginning, it's very, very unexpected. So this is roughly 2% of gain. Number one, and look at the error. The errors are very, very different. A lot of sounds, like very short phones using this trajectory model, actually I correct them. It's just because it has this co-articulation phenomenon. And those phones are typically wrong in deep neural network. We haven't done that yet. The next generation will correct them. Okay? And whereas for long sound, like some S sound, F sound, and some long vowels, this model, the deep neural net DBA model, I'll talk about later, typically correct a lot more errors than here. So the errors are very, very complementary. So the first time I look at the error, I say, gosh, that should be the way to go. And then it turns out that the more we work on that, the better it gets. The result is going to get. But anyway, so all these are, so at the end, so I'm going to skip this one. So the point of this is to say that there's a deep dynamic model. So at the end, I was so upset about all these switchboard results. So I said, well, why don't I just write a book, summarize it, and that's it. Okay. Now, that's about 2006. Now, I'll tell you what new, so this is fairly independent to begin with, but just one single click that makes things go into speech. Okay, that's related to the one I talked about earlier. So deep learning, so this is complete different part, okay? And then I'm going to see how they merge. So for those of you who are in neural network, you know that neural network has went through up and down a few times, right? So for this new deep learning, some people call it third generation neural network, some people don't. So now to give you sufficient background for this current neural network, deep neural network, I'm going to give you a very brief summary of this first generation. First generation is based on perceptron. And notice perceptron is still in use now, especially in NLP. Right? Every now and then I see NLP still use a perceptron to do learning. The advantage is very simple learning. There's no hidden layer, and the diagram looks like this. You can nonlinear unit here. You get just a linear, essentially it's a log linear model. So if people think about maximum entropy model, they all belong to the same category. And then this first generation ends around 70. By the book written by Minsky, and the book is called Perceptron. So I don't have time to go through all. For those of you who attended MIT, you typically. So actually, I took a class from him a long time ago, and he taught a class called the Society of Minds. He mentioned nothing about neural network, so you know how much he himself hated neural network at the time. Now the second generation neural network came around this time. That book is 1969. He wrote that book, and that was before my time. The story is that part, all the government stopped funding neural network. Because the book actually is a very nice book. It actually analyzed, it actually has a lot of examples to analyze the fundamental limitations of perceptron. Because it's one single layer, it's actually a linear model. It's like linear model, maximum entropy model belong to that. And also logistic regression is the same. It's a two-class problem. So you think about it as a softmax. So that first generation neural network you can think about as the final layer of neural network so far, without any hidden layer. Okay, now the second generation came along around 80s. So I think the major difference is that it adds hidden layers. Once you add these hidden layers, all the limitations discussed in the earlier book disappear. Okay, so like XOR problem that the first book said, no matter how smart you have, you can't even separate this XOR. So if you class one here, class 2 here, cannot do that. Now using this, you can show you can do it. So the fundamental algorithm to do this is called backpropagation. We talked about this morning, and there's a third author. Actually, I think they wrote a Nature paper that actually published this algorithm. And then it has, so in theory, it's very good. People even have the theorem prove that if this large enough, you can approximate any arbitrary function. I think that theorem is the hindrance for the progress for this whole thing. Because the last time I was in Singapore giving this talk, multi-layer. So immediate question coming out of the audience is that, we know the theorem. One layer can do anything. Why do you need to have many layers? Right? So one hidden layer, if you have infinite size, it can actually approximate any arbitrary nonlinear function. And that was done. That was a theorem proved in early 90s. But the proof that requires that, number one, you get infinite size. Number two, you get global optimum. Right? And none of them is true anymore. So actually, it's easy to rebuff this kind of argument there. I think, but the new deep learning doesn't solve global optimum either. It just gives you better optimum, which I'm going to tell you why. So it actually died effectively in late 90s. I think.
Why do you say it died?
Well, I shouldn't say that. I should say died effectively. Well, I know. Yeah, I know.
See what is exactly the difference between dying effectively and
Okay. Okay. Well, I mean, yeah, I agree. Yeah, people mention that this is a bit too strong a word. It's just not as fashionable.
No, I mean, so the tandem came in 2000, right?
Yeah.
Because I guess
But to me, tandem is not real.
well,
It's a pre-processing. Yeah, it's a pre-processing. Yeah, I agree. Yeah.
Element, and it's used just in about every DARPA system nowadays.
Yeah, I agree. Yeah, I should say that effective except for Hinnick's, Morgan's group. Yeah. Yeah, okay.
Say maybe it is dying. Is perhaps
Maybe that effective in machine learning community because I think in 2000, I think in 90s, a lot of people in neural network, right? Actually, I've been to NIPS in Vancouver almost every year. Now, I think in 2000 starting, all this kernel machine came along, very popular, and all this Gaussian process, all. And if you count how many neural network paper in.
But this is a problem of machine learning.
Yeah, I agree. Okay, I agree. Yeah, I'm sorry. Yeah. All right. So.
We started to use it in 1990.
Yeah. I know. So I should say that effective in machine learning with and very actively pursued by a few group, including Hinnick's group.
Look at EDF, look at
I agree.
Look at Bernal.
Bernal.
These people.
Yeah, I agree. Yeah. So this is wrong audience to talk. Yeah, I should modify the slides.
It should never be put out.
Yeah. Okay. No, in machine learning, it is true.
In machine learning, because you are misleading them.
Yeah, I agree.
It died in your community, but it was still.
Yeah, that's good. Yeah, there's a very consistent group of people. I think Hinnick is the leader, and also I think Morgan, and also three of you. Yeah, it's persistently, but the result has not been promising so far. Has not been. I would say.
System at DARPA, it is promising.
Has not been highly promising. Maybe that's the best way to do it.
Yeah. Because people wouldn't use it if they.
Yeah, I agree.
If it wasn't helping.
Yeah, I agree. Yeah, so I really should change that. Okay, then thank you very much for making comment. Yeah, I should have made that. Okay. Yeah, but this statement actually is accepted by machine learning. Every time I go to machine learning, they never dispute that. Yeah, that's important. Yeah. So it's a bit exaggerated. Yeah. Now that came along. Yeah. So one of the reasons I put this one in there is that because I want to show you why, it was kind of become unpopular in machine learning community. Right? Maybe the best way of do that. And one of the reasons, if you analyze this backpropagation, the idea is that you take the error, take an example, you can get a cost entropy error, or So in this particular case, I use a mean square error. You take derivative, you can see that the deeper you go, the more difficult it is to learn. So two equations can show you. So if you take derivative of the error function, objective function, with respect to the weight at the lower level or the deeper level, you can see that it becomes this is the response. This is the response. And this is this sigmoid function. This is the 1 minus sigmoid function, which tend to saturate. And this is another derivative. And this derivative also has the same form. So you get deeper and deeper level down here. You get many more terms of this one coming together.
But we talk about it over breakfast.
Yeah.
Where you can always stack the material perceptrons one after another in a cascade.
Yeah. Yeah. Maybe that's your trick.
One after another. That's what we were doing.
Yeah. So if you use that trick, that may overcome that problem.
Yes, that you don't get this problem, right?
Correct. Yeah. That's.
When you say stack, you mean that you train every layer or supervise?
Right.
And then you use those
essentially
You concatenate.
the output from one as an input to another.
Right, but they're trained separately.
They are trained separately.
And you freeze the weights before you move on.
You will keep the weights before you move on.
Yeah.
Basically, you just that's what we do.
Yeah.
Sure. I mean, this is sort of one of the basic innovations of the new resurgence in deep learning, I think, is to train regularly layer by layer with a stack bar.
But at the
Well, that's one of them. So my stacking network.
they
There's a second level is using the same idea. So this is the straight deep neural that doesn't use that. Right?
That is true, but as I said, I mean, you can always...
Yeah, you can do that. But you do that, eventually you still have to pipe all the way down. If you don't do that, you don't get as good a result. Yeah. Yeah.
I agree.
So,
I agree.
yeah.
Someone summarize the gist of this discussion?
Yeah, the gist of discussion is to show why second generation neural network died effectively for machine learning, prematurely. Okay.
Second generation neural network.
The second generation neural network looks like this.
Okay, and then deep networks.
Deep network.
Third generation.
Third generation. Then it's yet to come. Okay, it's yet to come. So this is 1, 2, 3. Okay. So prematurely become unpopular on that. Okay. Well, thank you very much. Yeah, the word heading is really precise. Okay, and with exception, blah blah blah. Okay, so you can see that the more deeper you go, the more you have these factors multiplied together. So if one of the layers gets saturated, that means that either if this one becomes 0, this will become 1. Or if 1 becomes 1. Yeah. So if you get saturated, this one becomes 1. Then this one becomes 0. Then the gradient becomes 0. Right? So that means you lose your learning signal. And the more deeper you go, the more chance that will happen. And that's why when people use the deep network in terms of architecture, not in terms of learning, okay? That's important. Yeah. The deep architecture is always there. It's just a matter of whether you're learning or not, okay? Yeah, that's a good point. Then you just never learn. You just, at the bottom, you just stay the same. Whatever you initialize them to be random, it's still random. So it just effectively become gone, okay? And people have very, very high hope in the beginning, during the second generation, it's going to work. But at the end, and people essentially just say, well, let's move to, support vector machine, to do other, more interesting things in machine learning, where you can have convex optimization problem. You know exactly how to optimize them. Whereas here, you never know how to optimize them. No matter how you do, it's all local optimum. So now it comes to renaissance of neural network, and that's some people call the third generation. So that starts in 2006. There's a paper in Science published by Jeff Hinton and his graduate student from Toronto. And he was, as you see, that he was also one of the pioneers in the second generation. And in his own word, he keeps saying that it's just a huge disappointment. Huge disappointment. He probably didn't know much about Linux and all this work, which still has something going on there. But you never see error rate drop by half, all these big things at that time. It's just limitation by technology. So he invented something called deep belief network. I really don't have to go through all this. This is pretty deep subject. And the paper, if you read the paper, it's very hard to understand. He told me why. In order to write science paper, there's a lot of politics involved. You have to do certain things. That's why he wrote the one it is. So, and also he kept telling me that I used to be a professor at University Waterloo. I worked fairly reasonably close to him, so we actually communicated quite a lot at that time. So the essence of this technique is that you pre-train each layer from bottom up, and each pair of layers is a restrict Boltzmann machine, and jointly fine-tune them all together. So this concept, you need at least 1 hour to go through them in detail. So I'm going to skip them, except to tell you that they're important. Okay, so I give you one slide to summarize this entire hour of material. So it goes like this. So the restricted Boltzmann machine goes like this. You think about it as a neural network, but the communication between this layer and this layer are bidirectional. It's not just from bottom up. So it can go up, it can go down. It can go up, it can go down. And this one can be formulated in terms of probabilistic model. Okay. And I think in his science paper, he never talked about all the details, just assume that all this. It's very hard to read. So this actually can be considered to be graphical model, bidirectional graphical model. Sometimes people got undirected graphical model. And the graphical model, of course, is characterized by energy function. He has particular energy function that model the interaction between visible layer. So in machine learning, they keep call that as a visible layer. In speech, we call it observation layer. So this one can be any feature. So one of the main premise of deep learning is that you can go back to the original raw data feature as much as possible, rather than using PLP or MFCC or whatever. You should do lower level. maybe get rid of the transformation, because if something that happened well, it can surface at a higher level in the deep network. And actually, we proved that. So we at Microsoft proved that it's true, at least for the cosine transform. You can get rid of cosine transform. Therefore, MFCC is not going to be dominant technique anymore. Well, it has been around for 20 years. Now it's officially not maybe that. Maybe I don't think MFCC will be around as long as people use deep network. For HMI, you still need to use the MFCC or the transformation, because your Gaussian mixture model, the Gaussian component require diagonal. Otherwise, it's very hard to compute. But anyway, so the restricted Boltzmann is essentially 2-layer of undirected probabilistic model. Well, I don't say that. No.
We are not using a text room.
Correct.
Don't do cosine transform, right?
Correct. If you don't use, correct.
Sorry, I'm just following.
Yeah, I know. A lot of people. It is that. Good, very good. I'm glad coming from expert, the inventor, that kind of transform is not required, right? But anything else? So actually, we are trying to go even further, try to get rid of filter bands. So this morning we have very good discussion. We have not been successful yet. There's the reason why. Well, it may be successful if all this learning, the one I'm talking about, can give some reasonably close to global optimum. I think all this will be that. The only thing left will be maybe waveform or maybe Fourier transform or something. But since we don't have any good architecture enough, we don't have any global optimum algorithm, we still have to combine knowledge together with the architecture here. But anyway, so once you have that, so this is there's a lot of material over here. So I'm skipping it quickly. The whole point of this Boltzmann machine is that you can do inference very, very efficiently. So this is one of the key things I learned from deep learning. Now in graphical model that I did at Johns Hopkins many years ago, and Microsoft is directed model. And the inference is very hard. So there's something called explaining away for those people who know Bayesian network. And explaining away is essentially generation is easy. Now, if you do inference to see what is the top, speech sigma, you have to do all this Bayesian, very complicated marginalization, which is typically people approximate them. And I believe that those approximation actually lose a lot of performance. Whereas for the bidirectional model, this is easy. You can even write, there are about 5 steps of derivation. In my paper, I'm going to show you. There's a derivation. It's about 5, 6 steps. You can actually do this is what's called the inference. Given this, you just compute sigma function. You actually get the probability of the firing over here. Okay, and then you can do the sampling over here to learn all this. And this is something a little bit subtle. You should read some of the papers here. Yes?
It's not that surprising to me that a big, honking, huge, unsupervised learning algorithm like this can replace PCA, right?
Yeah.
Which is what you're saying.
Correct.
But can it replace the null scale, and can it replace vocal
That's what I'm...
normalization?
Vocal length normalization has been replaced. So I'm actually working on that now, and ICAS will have a paper. So vocal track length normalization become one of the very simple steps in convolution when you add convolution concept into this. So people who are doing image recognition, people tend to use the convolutional network to deal with the translation invariance for the image. Now, if I limit the degree to which the translation is done, according to speech information, I actually can get better result than in vocal track normalization. Yes?
Let me remind everybody here, the beauty of local track normalization is that just a very simple one parameter can have in a model, which can control that little parameter, can have an enormous impact.
Correct.
Is that the same thing for the deep network?
A little bit more complicated than that.
A little more
More than one parameter.
I don't even know where the parameter
Yeah.
is probably what is that.
Yeah. But the architecture,
Really the power,
correct.
that was the power of vocal track normalization.
Correct. But that concept,
A lot of parameters, isn't it? Like, however many H things times.
so I'll show you all the number. So now, the more data you have, the bigger you can get. So now in our Microsoft system, 2,000, 3,000. You can never imagine that, right? And this lower level before is about in HMM. How many parameters here? 39. And you get, delta altogether 39 something. Now here you get 500. So we can afford to get big chunk of data. And he told me that in a lot of work that he's doing, he also uses big chunk. But in HMM, it's very hard to do, right? It's a standard HMM, you big chunk, you get all variability, right? It's much harder to do, and then he has a way of doing that.
Are you using null scale input?
Yes. Yeah. Not yet. Yeah, not yet. Yeah, we'll do that. Yeah, maybe 2 years. You see, maybe mail can be learned. Yeah, maybe it's not quite mail. Maybe it's, for different speakers, you may have different mail.
Why would you want to use deep belief network when we show how to actually learn the mail scale from data?
Correct.
In a different way?
Yeah, that's correct. But if you believe that this is the right way, right? It looks to be the right way.
I mean,
Well, I agree. Mail. It's premature to say mail will be gone, right? But it's very confident that cosine transform is gone. Okay.
You should just give this algorithm a professorship somewhere.
Okay.
We don't need this anymore.
Yeah. But anyway, so this is not the whole story. This is the shallow network. Okay. That you can show that. So what is in original DBN is that you can do stacking up. So let me see on this animation. I just make this a very nice animation. So this is hidden layer, and this is hidden layer. This is the input. So you learn something, and how to learn that? In 10 years ago, it takes infinite amount of sampling. So it's not tractable problem. So Jeff Hinton, he told me that by one time he just couldn't wait overnight. He just said, "Well, let's cut it off by just simulate 2 steps." And and then when he came back, he found that result is almost identical to just do infinite sampling. And then he hired some postdoc and graduate student to write a few theses to prove why it's useful. It turned out that if you do that, you don't optimize the likelihood for this model to generate data. You optimize some what's called the contractive divergence criterion. So which is not exactly the same thing you want to optimize, but it's reasonable. So that part is, it's just empirically work well. So once you do that, you learn this, and then once you learn it, you multiply this, you get this. And once you get this, you can treat that as the data. You do one more layer. So this one become observation, visible, and then you get hidden again, and keep doing that. You keep doing that. So once you do that, this is pretty much this is the rough shape of RBM. Okay. So these weights are all different now because you learn them differently. And now this is the label here. And then the next step is that after you learn all this DBN, so everything here is called a deep belief network, okay? After going through layer by layer. And then you treat them as the initial parameter for neural network, which are done generatively, right? So this generative. You make no use of data label at all. And that is a very, very good regularizer. It put the neural network into a spot where you can optimize much better than if you were to put random number there. Okay? Yeah, Tom.
What do you maximize?
You maximize.
At each level?
Okay, so this one, the ideal objective function is the likelihood. Just like hidden Markov model, you want to optimize likelihood. With respect.
The ultimate.
No, so far there's no label. So this is unsupervised. Just like hidden Markov model, you throw a whole bunch of data, you want to see what is the means of variance in such a way that likelihood is the highest. Right? It's the same thing. So, but it turned out that this one, so this one goes into long discussion. I probably this one actually can be shown to be effectively an exponentially large number of Gaussian mixture components, because every single node here, gives you a Gaussian mixture. So you get 2,000 units, you get 2 to the power of 2,000 is larger than the number of the atoms in the universe. So it's a very, very powerful model, but the learning is hard.
So it's like a single state model?
Yeah, single state with the weight tied in particular way, not precisely tied, and there is a formula that you can show how it goes. So it's a very powerful model. And then you keep stacking up without any data. So all the way up to here, there's no data whatsoever. So you can get the raw data, you do this, you get some feature. And that feature has the property that...
You mean without any supervision?
Correct. There's no supervision. Unsupervised. Up until this layer.
No, is it somebody else who is using auto-associative net here in place of this pre-training?
Netflix, what is that?
Auto-associative network?
Also, it's an alternative way of doing that. The Benjo in Montreal group is an alternative of doing that. It's an alternative of doing that. Yeah. So that actually, in the beginning, within 2 years, it's not as good as doing this. But later on, they fine-tune that is similar to this. So there are a few alternative ways of doing this. And this is the original way, and this is the way that in our speech recognition system. So now once you have that, the amazing thing is that you can just copy these DBN's weights and put them into neural network, into the second generation neural network, and then do the same backpropagation learning. and most of the problems that you encounter in the second generation disappear. And there are a few PhD theses written to analyze why.
The very last layer here
is a label. It's a label. In a phone label.
Okay, so what happens if you just didn't retrain the whole thing, but you only retrain the last layer?
Okay.
Would it be a big difference?
Yes. Yes. Yeah. Correct. The more you train, the better you get.
But
Yeah.
I mean, how big is the difference?
Yeah. Of course, this one. So retraining this one probably is the most efficient. It is. It has more. So doing this, if you're just doing this, you'll be like using, DBN to train perceptron. Right? But it's fundamentally limited in terms of what kind of problem you can solve. Right? It's the same problem. If you just doing this, cut off this, you can get very good representation of this. But you might be able to solve XOR problem because this one transformation already represents the new feature here. So but we found that we did all the experiments. How many layers you go, that depends on how much data you have. So now industrial deep learning. I'll give you a bit history. Okay, so in our MSR 2008, I actually reconnected with Jeff Hinton. I used to know him quite well. Actually, my first PhD student actually had Jeff Hinton to be the external examiner. He came from Toronto, coming to my to Waterloo to defend. So he knows speech quite a lot. I mean, he's a very intelligent guy. So we reconnect. After several years I was in Microsoft, we didn't really. He came to visit a couple times, but at that time he already published his deep learning paper. And he kept saying that, well, not many people pay attention to that because that was kind of the death, unpopular. In 2008, it wasn't still not very popular. Right? So it became popular, I think, 2010, 11, 12. It gets more and more popular. Actually, I should put Yang LeCun here as well. Yang LeCun, Jeff, Ben Zhou, they all do that together. So there are about 3 groups. Yeah, Yang LeCun is he's doing mostly in vision. Yeah, I should put his stuff here. But Yang LeCun is doing some very different things. He's mostly concentrating on what's called the convolutional neural network. It turned out for convolutional neural network that because weights are tight already. That problem is not as severe. So he has been doing that all along, but it's very unpopular for many years. Most of the people actually like convex optimization, like NLP people, and like speech people. We don't care convex a lot. Right? Our hidden Markov model, Gaussian mixture model is not convex anyway, so we do it anyway. NLP NLP probably doesn't like non-convex problem either, does it?
No, we have that non-convex problem.
You have that one as well. Okay, maybe anything in between. Speech and neural net are about the same camp. Right? We like to solve the problem. We don't care how convex. And machine learning, there's a group of people doing convex for years. They just everything. Even in my organization, a few neighbors, anything that's not convex, they don't even want to touch. Because they cannot analyze, they cannot prove theorem, they cannot do a lot of things they cannot do. Here, speech is very practical, just like neural network, and maybe a part of the NLP. So in early 2000, so actually so at that time he actually told me that that's a really cool thing you really have to know. So he showed me to his poster, just beautiful diagram, to show. It's a very, very small task. So I said, well, it's worthwhile for me to go back to explore. So I look at MNIST, some digit problem. Actually, it looks very promising. I look at receptive field to see, it really represent, form and burst. They're all coming out very nice. If you analyze the hidden representation here. So I said that, well, so I invited him to consult with me. He spent 1 week in my office. So we actually, so this actually the time we realized that, well, we shouldn't do capture anymore because every time you do capture, you can't even interpret what it looks like. I mean, you have to, I know how to do special reading. I spent 1 year in Victor Zhu's lab. So I went through every single special reading stuff. So after I returned from his lab, so at Waterloo, we did about 5 years of special reading in my group. So every single, and look at spectrum, roughly I know what it looks like. Now, use the capture, it's very hard to see. So I said, well, let's do, everything in spectrogram. And that's really consistent with deep learning's original idea, coming back to the more original feature. So we collaborated in applying deep belief network, initialized deep neural network. That's what it means. Okay. So they're all different things. RBM is the big building block of DBN, and DBN is a component of DNA as an initialization. You still have to use backpropagation to get DBN work. So these are the relationship. And then the first experiment we did was to, and then actually at that time, we decided to have a workshop in 2009. So Jeff and my colleagues, we actually co-organized this workshop. So this workshop took place in 2009, and this is actually the beginning of deep speech recognition. So for those of you who went to NIPS, you normally remember that at the end of the NIPS workshop in the banquet, they usually ask the organizer to give some funny summary of the whole workshop, and that's the summary I'm going to show you. So this is called so the organizer called that speechless summary presentation at the NIPS speech workshop. Okay, so in the workshop we didn't say anything, we just show this. So that's all we did. Yeah. So I was told that you're smart. So this is like Microsoft, this is like Toronto. Okay, and he said, okay, because I'm deeper. Okay. So I gave actually a talk at one time, and people totally got lost. He said the only thing they remember is a carrot. Yeah, and that's why. Okay, can you understand speech? And then Toronto guys will say, yes, you bet we do. They want to do phoning. Okay, so I said that it's a nice first step. Okay, they said, what else do you want? And then we recognize noises, speech spoken by unknown, and then we can work together. And then we hire him for a while. And then at that time, those are the keywords, about 3 years ago. And most of them are not useful anyway. A few things are useful. Scalable is important, this is important, this is important. We haven't done that yet. And that's it. And that's our presentation. So organizers say, well, speechless. Anyway, so let's show you a little bit of history. Okay. Now, what's the key insight through this work? Okay, my time is almost up. I haven't gone through half of them. I go quickly. So we have until 1:30, right? Or 1 o'clock? 1:15? Okay, so I'll go quick. So the key insight, how it connects, how this deep neural network connects to the previous one, deep hidden dynamic model. I think the key is what comes over here. So deep speech model should run bottom up rather than top down. And I think this morning I talked with Jason. Why is it that deep Bayesian network is difficult? I share exactly the same problem, 1, 2, 3, 4. So it's through the experience of deep neural network that I realized this is really difficult. So you should run bottom up, not top down. So the green here means do it, and red means don't do it, okay? So not top down. Top down is very hard to do because eventually you have to do bottom up, right? So if your model is top down, then when you do bottom up, you get this explaining away factor, problem. So you cannot. It's just very hard to do. And then you can also avoid a lot of approximate learning, variational learning, and then we use a fixed long temporal window rather than using hidden dynamics. So the project I did here we use hidden dynamic to automatically parametrically represent the dependency in the frame. Okay, sorry. It turned out that this is a bad idea. So the better idea, So let me do that. So the better idea would be just use the long window, and that's a hack. That's a hack. Okay.
It's not a good hack.
It's a good hack. It's a good hack. And to me, so this morning I talked.
It's not a hack.
Yeah.
So basically, allow yourself.
Yeah, I know. But you can see that there are much better way of doing this. More principled way of doing that. Yeah, I agree. So this is better. And this, but this originally is supposed to be principal approach. For this, I can capture the dynamics throughout the whole sentence, just using very parsimonious parameter to do it. And that's, mathematically really elegant and conceptually it's very good. But in practice, it never works well. So this is good. Yeah, I agree. Yeah. So Henrik has been doing that for years. So we learned that from you. And then, co-articulative model, mathematical model, and also, so if you do this, then the difficult decoding problem in hidden dynamic model cannot be temporarily alleviated. And that's also a hack. So all the good ideas, if you don't implement them right, it's gone. Nobody pay attention to that. And mathematics is beautiful. I wrote a book on that. People love it. And my people in my organization, they say they ask me all questions. But I think to make it work, you really have to go, not a hack, but also how to elegantly combine a good theory with a good implementation. Now the net effect of doing this is that we can use DNN, deep neural network, as a feature extractor for HMM to replace GMM scores. So GMM is that in speech, that's for sure. Agree? Okay, agree.
Saying since 1990.
Since 1990, okay. Since 1990, okay. Yeah, it is. And nobody, as long as you do deep learning, don't ever use.
But you're saying you do research on scores.
Yeah, correct. So HMI is not that yet. But the last part is to show you in a few years, HMI will be there. I'll give you some. So all the major pillars of speech recognition is that one by one. Okay, that's good. That's very good progress. So, and that actually comes about because of tight integration between our field and machine learning. That's modern machine learning, not the theoretical machine learning. People just prove some bound and theorem which are useless.
I think is which you have to get rid of is the bit research.
So there are ways of doing that. So I'll share some lines on that. Yeah. So probably you're doing that already. Yeah. Everything I talk about here has thought about. So that's great. So the net effect that we use the feature extractor for this one and replacing this. And the consequence of this is that you can go back to the filter bank, towards raw feature rather than using MFCC. Well, there are two reasons. One is that, number one, it's much easier. Number one is that you don't need to worry about correlation anymore because DNA handles correlation perfectly well. Okay, and therefore you don't, need to do any additional processing. And number two is that anything that is good, if this correlates, the correlation is good through cosine transform, it will automatically appear somewhere in the layer. Because it's a deep. If it's a shallow layer, you won't be able to do that. Right?
How about the MFCC? You're going to solve that too.
All right.
How about the
What do you mean? The end?
of the MFCC?
The male FFC, male. We are working on that. We don't know. Right. I think philosophically you can do it. If I can do global optimization, I'll get it right away. So far, I think the quality of optimization and how much you can give of this, is related to each other. So actually,
If I may comment, if you just do linear rotation in the frequency space, you do get a Mel transform, but you don't do it globally. But if you just say the volume size of classes and you do LDA,
yeah, LDA.
at the Mel scale.
Yeah, I see. That's interesting. Well, actually, HLDA, we did that.
Yeah.
We actually, if we add HLDA, we don't gain much. We did that. Yeah, so HLDA. That kind of said that, this learning already embodied part of the HLDA. Right? So a lot of, little tricks, in speech recognition. Remember, in speech recognition, the IBM built that Deng has been involved. Even in Microsoft in the past, before we did this, step 1, step 2, you do this FMP dimension, everything can be gone. It's just because adding a few more layers is all gone. So my life is much, much easier. I don't have to worry about all these little steps, and then the result is much better. So this really is the power of learning. Right? If you learn well, a lot of things, heuristics, including what's called the arbitrary length normalization. So now, all this to me is for efficiency reasons. Because, all this, in theory, the sticky network can do all this if you learn them well. But in practice, you can do it. So you have to use a different paradigm, like a neural network, to help you to do this. Now, for effective reasons, and this is very important to I learn. So when we did this in '98, and also in part of my Microsoft work, we did parsimonious models. We said that, the small is beautiful. Right? Everyone says small is beautiful. You use a small parameter, you hope to capture the essence of the, and then you don't have to worry about overfitting. But when you use the parsimonious model parameter, speech is complex model. Of course, you lose something. We know we lose something. We just want to make it beautiful. And now hidden neural network said, I don't care. I use a massive number. Now I get a computer to get the computer. I get GPU, can do it fast. Just a massive number parameter, I think, can win over parsimonious model. And that's.
You know about big dumb.
Yeah, exactly. Yeah, okay. That probably come from there. So you realize that long time before I did. Oh, that's very good. Yeah, that's done. Right. But at least you acknowledge it was done. But now it's not as done as before. Right. And also another very important lesson I learned is that compared with the DBN is that DNA has a distributed representation, whereas the hidden Markov model, the one our current technology, and also hidden dynamic model, or all this has a class space representation. And in our current technology, HMM, GMM, there is a concept that this much weight, this much Gaussian means and variance belongs to this class, right? This Sinon. And then the other part belongs to the other. That's not distributed representation. Whereas the EDN, each weight matrix is related to all classes. And that's called distributed representation. That's what brain is doing. Right? The brain actually has the neurons that represent. So some of the brains can do, like visual cortex neurons. If needed, they can be turned into auditory. They can respond to auditory sound. Right? Like the motor neuron can respond to this. And that distributed representation is very important as well. So all of those are missing in our generative model, in our speech technology for the last 30 years. And I think that's an important lesson that I learned. But anyway, okay, so now how industrial deep learning started. So since originally we got a good result with Jeff Hinton, and more people in our group now, it's about 2 years to started doing speech. Now this year, in the summer, almost every single intern in our group is doing deep learning in different ways, overcoming this problem, so slowly people are moving. And then in 2010, the first success of bottleneck feature coding using speech spectrogram. Actually, I'm going to show a paper that we wrote together on this. And then about 1 month after that, we showed that in large vocabulary, and we wrote the paper in here. And that is the time that Patrick actually moved to Google, and he actually knows all this. And Google actually catch up very quickly. And then in October, my colleagues, Deng, actually collaborate with Microsoft Research in Asia, France side. And they actually decided that, wow, that voice search has about 50 hours speech. They said, wow, since now GPU is all set up, we have to do benchmark. And they decided to do switchboard tasks. And then they published a paper in 2011, just very quickly, just a few months. They did that, and that actually raised a lot of awareness. Many people realized that now for switchboard benchmark, it's useful. So this is the paper, the first paper I wrote, published in Interspeech 2010. So I actually did this work with Jeff Hinton and with a few other people helping. So this is to use the autodecoder. This is one of the alternative to this DBN. Well, this actually uses DBN to do this. So the idea is that you get RBM, you get another RBM, I do 2 layers. And then you flip it over, and then you make the input to be the target. And then you make this one to be big, and you make this to be small. So this is called bottleneck feature. And then you do backpropagation. And when you do that, that's amazing. I use only about 32 bits here. I can represent this, how many, maybe a few thousand. In that case, I use 13 frames with the 250 FFT parameters. It's about just tens of thousand bits. I can virtually reconstruct using just 32 bits to construct this. So I had a whole series of experiments done. So number one, I was really happy about spectrogram. Well, actually, this spectrum is not even male, but I think for discrimination, male would still be important. So this is published over here. And then I think in last year's ICML, Andrew Ng sort of extend this concept into multimodal. So what he did is that, so this part is the same. If you cut off this video part, it's exactly the same as this. And then he put the video information here. And therefore, this intermediate representation becomes bottleneck that encapsulates both audio and video information.
How large is the bottleneck in this case?
The bottleneck, in my case, I used about 32 units. In this unit, I think he's a 50 or 70 something. I forgot. Yeah. So that was actually he did. And then look at everything here is unsupervised. There's no label whatsoever. And what they did is they use this to other recognizer. I think in Andrew Ng's group, they typically use linear SVM, hoping that whatever deep learning that you get from the feature can be useful for simple classifier. But we tried that approach. It's not as good as the one using full end-to-end learning in deep neural network. But anyway, so this is the paper that we publish. That's on my website. It's the first case success of using deep neural network for it's a pre-trained. That means using DBN to train for large vocabulary speech recognition or voice search tasks. So the key innovation for this work, and this is actually considered to be the start of industrial scale deep learning, is that number one, we scale the success from small academic tasks and attempt it into large industrial tasks, and we actually now use that for all our product, speech-related product. And then we grow. Now this is important. This is something machine learning people won't be able to do, only speech people can do. We grow a very large number, a very detailed DNA output neurons. Therefore, our output neuron is essentially, in our experiment in this paper, identical to our HMM output. So in other words, context dependent of state. So the states in HMM large system become just copy that down to be the output, and which wasn't done in the past. In the beginning, we didn't believe it's going to be really good because number one, it's huge. It's 9,000. That's a lot. So 9,000. So the output is 9,000, and the layer up to about 2,000. You got 27 million parameter just by doing this. And it doesn't matter. Just train them, and it works. And then another very important contribution, and this is something that I'm really, really happy. One of the reasons we do this is because we don't want to change our investment, Microsoft investment, for the decoder development. We got a whole team of people doing decoder. And remember, Microsoft bought Entropic, right? So HTK went to Microsoft. And partly it's because we need to have decoder in addition to engineers. And we invest a lot on decoder development. If we use identical things over here, all we have to do is training. And then in the decoder, change minor things. Just replace, just in the decoder, we just get rid of Gaussian mixture model to replace the score from, we have to normalize by prior. Right? If you divide the posterior probability from neural network by prior, you get quantity proportional to the likelihood you can plug in to HMI, to the standard HMI decoder. So we still, so therefore we can do first pass decoding. If we knew that trick in 1998 workshop, we should use that. So we can do first decoder. We'll probably get much better gain than the way we did for, for second pass decoder. And this is a very important trick. So we did that. And then we leverage existing speech recognition system decoder software at Microsoft. We make effective 12 years of investment in this area. So company is very happy about that. All we do is that our research staff can just, directly, they don't care about how the training is done, as long as it's good. Now, for decoding, it has to be real time. They say that, wow, that's cool. They don't have to spend time to do all the coding for learning. So that's nice, a very, very good, important contribution. I think since all this, this is actually published in the special issue, came out. And it's a simpler and equally effective. Well, this one I don't have to, so you actually can do something simpler training than DBN. So, but DBN is very safe. If you use DBN, whether your data is large or small, it all work. Now, if you have a very large amount of data, like in our case, we can do something simpler than that. So, which I'm not going to go through. So this is our architecture. So we have, this is, HMM state. Now the HMM state doesn't have any Gaussian output distribution anymore. Okay, 5 more minutes. Okay. But anyway, so this spectrogram, big window and deep, and then we tie all the weight together, and each of them become the weight, and then we do decoding. That's how to go. Okay, success. Okay, so this is the paper that I wrote with Jeff Kingdon with a whole bunch of other co-authors. So this is the, let me go through quickly. So for switchboard, in our Microsoft, so actually my colleague actually did this experiment, the one I told you in Microsoft Asia. The error rate dropped from, that's Gaussian mixture model, from 23 to 16. And for about 300 hours speech. Now we recently expanded to 2,000 hours speech. This error dropped down to 14%. Now Google did much more aggressive experiment. They actually use about 6,000 hours of speech, and the error rate dropped from 16 to 12%. Okay, so that's the number published in this paper. And this paper is going to appear in about 1 month. I heard that it's already printed now already, so we can go to yeah, already. Oh, great. So in my website, you can see that as well. Okay, and this is the, so this one I think I give you some back. So this is the number coming from NIST, right? So okay, forget about everything. So this is switchboard. Remember, we are doing something here, many years ago. Look at that. So I believe in this figure, nothing going on here. So I do this. Fair? Okay. Now this one coming down here, 1 single year we did that. So this one about the human is here. Maybe do two more innovation like this, we'll probably reach human. Okay, so this is also important. So this is standard Gaussian mixture model as a function of training size. So this is from Cambridge University a long time ago. I think this is part of the figure coming from ears. Now DNA going much steeper. Okay, so how far do we go? We don't know. Okay, we can't even do that. Now we are, we have the better infrastructure. So getting this number takes about 58 days. Doing 4 GPU, doing that. So how to do that? Now IBM recently got some very good results. So I don't have time to go through. Let me go quickly. So Microsoft product, a whole bunch of, and then this Google. Everybody saw this Google's announcement that actually in technology review, they actually said that speech recognition is the first service to benefit, using this deep neural network technology. And other areas of success, so everybody agree. I think this is from machine learning community, okay? They actually all agree that this is the first case success of deep learning. Now, in the recent, just 2 weeks ago, there was a, I told ImageNet computer vision competition similar technique win a big margin. There's additional technique apply. And Google use this service. And language modeling, I talked with a few people there. I don't have NLP. It's just beginning to see the success. Now, next way. Skip this. So this idea is a little bit like a Henning idea, doing stacking. Okay, so you actually get the output, and this is image recognition, the one I did, 3 years ago, and it's huge. I get about 200 layers. I still get that. Now for your stuff, you usually do once, right? And then you pass that to the recognizer. You can do many times. That's something so I've done. And then you can actually do some, we also have a version called the tensor version. Essentially, you can model correlation between the two. And then you also stacking up. A lot of good things you can do. And this we even apply, so in InterSpeech we have paper tensor version of deep neural network. You actually can model correlation because the standard way of doing neural network is that you lose the correlation directly. You use the indirect. Here you can do direct pairwise correlation. And then recently we actually we extended this to the kernel version. So the kernel learning and deep learning can combine also. So we actually, it's in fact like the infinite size of a neural network because kernel trick allow you to do that. And this is the result that we are presenting in about, I think, in December. So when I use this network, I work with my colleagues here using a kernel version of network. Look at this, the baseline. This is the baseline held for a long time. This is the task for speech understanding. Cut error almost by half. And people just love it in the company. And the experiment is so easy to run, not like speech. For this one, they get about 1 million samples. They feel it's very large. As a kid, give me more data. And speech, typically for timid, I got 1.1 million samples. This is a speech understanding task. I did with the the task is, the output is about 25 classes. So it's like, how may I help you system? So people talk, and then you want to classify to one of 25 classes. And then and the label is expensive. So they say, I can only have about 200,000. I say, oh, that's perfect for kernel. If you get about a few million, then it becomes difficult. So the error is, so we have this paper to be released, and the error is big, compared to, and this baseline number is coming from Gohan and Deng. You know this part, look them SRI. They're actually expert in this one. They actually use the boosting together to have baseline. This is low health baseline. So I think in ICAS we have paper together to use non-kernel version of the stacking net. We get some error reduction. Now when I apply kernel version, we get much bigger. So I think that's pretty much what I have. Some more important innovation to come. So no more temporary fix in modeling dynamic by HMI. Okay? I don't like it. You don't like it. Nobody likes it. And we're going to do to solve the problem. And then one of the things we are doing now, segmental model, and also we do deep recurrent network. It has long-term memory. It's much harder to learn. And then better HMM training method, dropout method, the one I mentioned to some of the people. And that actually is the one that, and so I tried that. Within 1 day, I was able to port that to our speech system from Vision. I got a gain as well. Now, so just to, not to advertise, just to let you know that I'm organizing this ICAS 2013. There is a special session. Don't ever miss that. So the name of the session is called New Types of Deep Network and Learning for Speech Related Representation. So Jeff and I are organizing this. So we are actually going Benjo, a few other people who are also in the field, from related field. They are doing music, sequence recognition. They all come. They all already promised. They already accept our invitation to write paper over there. I think that's all we have. Thank you very much. Okay. Questions?
A couple of minutes for questions.
Yes, please.
So you had a slide where you're saying that parsimonious is this beautiful dream of the past. We don't need it in terms of number of parameters, but there's still reason to have it, right? I mean,
Correct.
You're dumping a huge number of parameters into
Correct. Yeah, I'm not happy about it.
You need thousands of hours
Yeah,
to train it.
correct.
Right? Like if that's a reasonable expectation
Yeah.
for a given application, then great.
Yeah, I agree. Yeah, I agree with you. But if the model is accurate, if you don't need to have all this approximation to do efficient inference, I would love to have a parsimonious model. Right? And that's our original. So it's just a little bit too 10 years ahead of time. Right? But still not accurate enough. I haven't actually studied too much about speech dynamics. If you do neural modeling and can structure the model in such a way that reflect the real neural processing, I think that will be a good direction to do. But make sure that decoding should be reasonable. My experience, the first pass decoding is very cool. I mean, if you don't do that, you do experiment, industrial may not like it to begin with. Well, maybe academic is fine, but industry will always want to do first pass. Now, for segmental model, for recurrent network, we'll also shoot for first pass decoder. And that's difficult. If you do second pass, it's fine, but your lattice has to be very good. Otherwise, you will lose something. Yes. Okay. Any more questions? Yes, question.
I don't quite understand what's inherently. What's the inherent property that's occurred only in the belief networks or these networks that allows you the.
So why is it that?
The question is, I don't quite understand why you say that this is the kind of network that helps you with DCT and.
Okay. Yeah, correct. Well, actually, okay. So let me see whether I have a slide here. Oh, yeah, I might have the. Oh, I don't have a slide. Yes. Okay. In order to do vocal trail length normalization, this network cannot do it. I have to add additional layer, and that layer has to have some convolution within certain constraint, which I don't have that here. Yeah, actually, I thought I have it in the backup. No, maybe I didn't put it. And then using a limited range convolution, pretty much like what Jan LeCun has been doing on image. But don't do that too large. If you do that, you lose it. Do it in such a way that you can trade off between the invariance due to speaker difference and the discrimination is the key. If you do that too much, you confuse different sounds. So that's a trick. So you have to embed good speech knowledge there. So in ICAS, I will have paper on that.
Basically, you can say with normal beats, there is no inherent property of TBN.
Correct, but you have to learn that well. Right? You have to get to learn. Yeah, exactly. So for the normal MLP, you can do that, of course. But that concept has not been explored. So convolution has not been explored in MLP before. Right? Because if you are convinced that it's very hard to learn, why do you have to invest so much effort to do all this detail? At the end, you're not able to learn that well anyway. I think.
Since DCD is only a linear transform.
Oh, DCD is easy. DCD is very easy. Correct. DCD is easy. Yeah, I'm talking about virtual normalization. That's nonlinear process, and then you cannot. So that nonlinear process cannot be simulated by sigmoid function. Okay, and I think that's the key. Now for DCD, you can do it. Okay, and then another trick that I haven't actually told you, which I myself is very happy about this, is that despite all this success, we still have to keep delta parameter. This is the same thing over here, right? DCT, so cosine transform can be learned, and actually can do better thing because it may not be fun. Now for delta parameter, you might think that that's all linear. It is linear if it's a large window. If you get to them, you lose it. We try so many experiments, and I can even manually design the weight for the linear layer, so that I don't need to do delta parameter, right? Because it's all linear parameter. I just set the weight, sparse weight. I can do better than just train the whole thing. And that shows that there's a lot of room to correct temporal window. Now we do the same window, right? You get the same window, so you get about 5 more windows to do that. And I manually do that, and I freeze it. I get identical result with the delta parameter. Now if I train the whole thing, I typically get worse result. It's just that the learning, still not. I mean, so that's one reason. If all things can be done, in convex learning paradigm, you can gradually approach global object. All this problem will be gone. At worst, you get identical result, right? But now it's getting worse. So there's a long way to go, right? It's not just it's not just this. So I believe this paradigm is more promising than the conventional one that we did many years ago. Okay. Okay, thank you very much. Yeah.
Thank you very much.